Colleagues, thank you for the opportunity to present on behalf of an extensive R&D team. My name is Chris Berndt, and the points of contact for this presentation are Mr. Pham and Dr. Ang. Our presentation addresses the challenges and opportunities that thermal spray offers for bacterial mitigation. It addresses surface engineering and manufacturing and how these intersect with the biological sciences. First of all, please join me in dedicating this presentation to the healthcare staff and essential service personnel who have been at the front line in addressing the COVID-19 pandemic. We acknowledge their generous devotion and dedication, which has been truly inspirational. We thank you. As the first speaker for this global event, it is important to set the scene and emphasize the critical nature that biofilms and biofouling play in our everyday lives. Slide 3 illustrates where the biological interface with the local environment can lead to poor medical or industrial outcomes. The table lists 3 manufacturing sectors that exemplify a cross-section of societal needs. Some summary points follow. 1. Infectious biofilms impact our quality of life, our health, and our lifestyle. For instance, if you have a toothache, then you have experienced the adverse influence of a biofilm. 2. Industrial biofouling impacts the bottom line of productivity. If you experience clogged drain pipes, then there's the likelihood that biofouling is the cause. Thus, the first summary states that our aim as technologists is to control biofilms and biofouling by understanding their science. So let us define and distinguish biofilms from biofouling, as shown on slide 4. Both mechanisms represent a continuum of biological growth. The figure shows a transition from reversible adhesion of bacteria to irreversible adhesion. The reversible region in green ranges in seconds, whereas the irreversible adhesion can range up to months. An important point is that the biofilm process transitions from reversible to irreversible. Thus, the take-home message is as follows. If bacteria attachment can be controlled by clever surface engineering, then films and biofouling can be disrupted. Thermal spray coatings have demonstrated this ability to be disruptive, as will be described in the following discussion. The disruptive nature of advanced thermal spray manufacturing is shown in slide 5 for high velocity oxygen fuel coating. This collaborative work was sponsored by the Defence Materials Technology Centre. The industrial customer dictated the need for a superior wear and corrosion-resistant surface for marine environments. The existing benchmark was an atmospheric plasma-sprayed coating that exhibited a surface roughness of 0.26 micrometers. This coating within the environments showed a very aggressive percentage cover of biological growth, both in moderate and tropical climates, as shown by the red columns in these 2 figures. The success of our work was founded on a composite feedstock that was designed to have high deposition efficiency, low as sprayed roughness, an ability to be super finished, and excellent corrosion wear characteristics. We were successful in reducing the biofouling significantly because the intrinsic surface characteristics were customized for this application. This is shown by a dramatic decrease in percentage cover of biological growths within the 2 marine environments, as shown by the 2 columns. Thus, we have learned how to interrupt the mechanism of bacteria attachment, and slide 6 shows results for cold sprayed coatings of 4 materials that have been composited with an antibacterial agent. The results for zinc oxide with aluminium metal are shown in yellow. The antibacterial nature is demonstrated. The supplemental slides to this presentation show further data for the green, blue, and orange composites. The point is that we have tested a wide range of metal plus ceramic and metal plus ceramic and polymer composites on a variety of substrates that have demonstrated similar antibacterial behavior. The antibacterial character increases with the functional additive. Antibacterial materials can also be thermal sprayed by employing liquid feedstocks as shown in slide 7. The chelating agents of polyvinyl alcohol, citric acid and oxalic acid have been used. These chelating agents react with cobalt ferrite nanoparticles to form a stable water-soluble complex that can be used as feedstock in the form of solutions or gels for liquid thermal spraying. The deposit forms a characteristic splat structure where the surface roughness depends on the chemistry of the liquid feedstock, as indicated by the topographical features shown in the central panel. The major outcome is that E. coli survival is significantly reduced. Thus, coatings and films can be designed for antibacterial functionality. It becomes apparent that there are several mechanisms for effective antibacterial and anti-fouling outcomes, as illustrated in slide 8. The bacteria are represented as blue ellipses. These bacteria interact with a surface that has distinctive chemical, physical, electrical, and topological features. Now here is, literally, the million-dollar question. Do I have your attention now? I ask you to prioritize these 7 surfaces in order of their spray capability. That is, can thermal spray create such desirable features and bulk architectural morphologies as indicated by these 7 cartoons? This is the opportunity and challenge that is referenced in the title of this presentation. My short answer is an emphatic yes. Yes, thermal spray has the ability to create such features, as well as other interesting microstructural artifacts that may be of commercial use. The longer answer for discussion and critique purposes is as follows. Mechanism 1 takes advantage of the intrinsic porosity and crack networks of thermal spray coatings. Mechanisms 2 and 5 take advantage of nanoparticles and knowledge concerning spray tables. Mechanisms 4, 6 and 7 can be referenced back to the van der Waals adhesion mechanisms proposed by Professors Matting and Steffens in the mid-1940s. Some of these mechanisms have been operative in the case studies shown in the earlier slides. A very recent case study from our lab is shown in slide 9. The 3 materials have been thermal sprayed: the traditional hydroxyapatite and 2 novel strontium-based composites designated as SRA and SRB. The top 3 images show S. auroris bacteria on the surfaces of these 3 substrates. The bottom 3 images show the microbiological results, and since these are unfamiliar to the traditional thermal sprayer, let me provide a simple interpretation. First, green represents live bacteria, red represents dead bacteria. Red is most desirable, since we desire antibacterial response. The proportion of red and green represent the relative adhesion of the bacteria. Therefore, the biological inference is as follows. The strontium A and strontium B materials kill bacteria to a greater extent than the hydroxyapatite. There is more red than green. And material strontium B has less adhering bacteria than strontium A, which is an attribute. So a major outcome of this research is that alternatives to traditional thermal sprayed hydroxyapatite are on the near-term horizon. As we draw to a close, let me present some key take-home messages on slide 10. First of all, thermal spray is a recognized manufacturing technology. There are a vast array of impossible materials that can be sprayed as coatings and films. The bulk structure and surface properties can be deliberately designed for specific functionalities. The bottom box refers to antibacterial needs. The focus is that these mechanisms and other desirable attributes can be tailored on the basis of thermal spray science. Again, referring back to the title of this talk, the challenges and opportunities are immense and ready for harvesting. In closing this presentation, the authors thank the Thermal Spray Society leadership for their vision in organising this global event. Their foresight and planning is appreciated. We can also plan for the day when we present the longer talk in a face-to-face environment. Finally, our R&D is a team sport. Many disciplines, many universities, many labs, many cultures, many companies. We are always open to collaboration since our team believes that we are stronger when we work together. Keep well and keep safe. Thank you.